Your smartphone is powerful, but quantum computers? They're on a whole other level. They're not just faster, they think differently. But what is it really? And why is everyone talking about qubits? Today we make quantum computing make sense, no advanced math required. Your phone is a wonder of modern technology. It fits comfortably within the palm of your hand, a sleek gateway to a world of information. It runs complex games, navigates your journeys with satellite precision, and connects you face-to-face with loved ones across the globe. Yet, a new kind of machine is emerging from the world's most advanced laboratories. This machine has the potential to reshape our world in even more profound ways. These powerful devices are called quantum computers. They are not simply faster versions of the computers we use today. They do not just execute instructions with greater speed. Instead, they operate on entirely new principles. They literally think in a fundamentally different way. This unique way of processing information makes quantum computers incredibly exciting. It opens doors to solving problems that are currently impossible for even the most powerful supercomputers. The concepts can feel strange and counterintuitive, like science fiction. The goal of this essay is to demystify quantum computing. No complex mathematics, no dense technical formulas, just clear ideas, simple analogies, relatable examples. The reason this topic matters today, on October 20th, 2025, is that quantum computing is moving from theoretical physics into practical engineering. Understanding the basics now is like learning about the internet in the early 1990s. We will begin with the classical bit, then meet the qubit, superposition, and entanglement. Before we can venture into the quantum world, we must first understand the foundation of all our current digital technology. Let us meet the humble bit. The word bit is short for binary digit, and it is the most basic unit of information in classical computing. A bit can only exist in one of two possible states, 0 or 1, like a light switch that is off or on. There are no other options. Everything your computer, phone, and tablet does is built upon this simple binary system. Every photo you take, every email you send, every video you watch is, at its core, an enormous sequence of zeros and ones. A computer's processor is a massive collection of microscopic switches, called transistors, that flip on or off to represent bits. To solve a complex problem, a classical computer follows a linear sequence, checking one possibility, then the next, and the next. But for some challenges, this approach is a crippling limitation, like finding a specific grain of sand on a vast beach. For problems with astronomical possibilities, molecules, or global logistics, we need a new kind of information carrier that can explore many possibilities at once. This brings us to the edge of the quantum realm. Now, let us leave the familiar world of the light switch and enter the strange and wonderful realm of quantum mechanics. The quantum equivalent of a classical bit is called a qubit, short for quantum bit. Like a bit, a qubit can be a 0 or a 1. If we measure a qubit, we will always find it in one of these two definite states. This is where the similarity ends, however. The true power of a qubit lies in what it can do before we measure it. While a classical bit must be either 0 or 1, a qubit can be 0, 1, or a combination of both states at the very same time. This is called superposition. It is not 50% a 0 and 50% a 1 in a statistical sense. It is simultaneously both 0 and 1. By harnessing superposition, a single qubit can hold more information than a bit, and as you add qubits, the computational space grows exponentially. This sounds like magic, but it is real physics. Electrons or photons obey quantum mechanics. With lasers, magnetic fields, and precise tools, scientists put them into superposition to compute. A classical 3-bit register holds one of 8 values. 3 qubits can hold all 8 at once. With about 300 qubits, you could represent more possibilities than atoms in the known universe. To make the idea of superposition more concrete, let us use a simple analogy. Imagine you have a coin. On the table, it must show heads or tails. This is like a classical bit, 0 or 1. There is no in-between. Now spin the coin. While it is spinning, what is it? Heads? Tails? You cannot really say. The spinning coin is a blur, a dynamic state holding the potential for both outcomes, a mixture of heads and tails. Measuring a qubit is like stopping the coin. As soon as you stop it, the coin is forced to choose, heads or tails. Similarly, when scientists measure a qubit in superposition, its quantum state collapses into a single classical value, 0 or 1. The power of superposition is available, while the qubit remains unobserved during the computation. Classical computing works with coins lying flat, definite heads and tails. Quantum computing works with spinning coins, manipulating probabilities and relationships between them. Only at the end do we stop the coins to read a final answer. This ability to compute on possibilities is the source of the quantum advantage. Section 5. Quantum entanglement, the spooky connection. Superposition is powerful, but it is only half of the story. The second key ingredient, entanglement. Einstein called it spooky action at a distance. Entanglement is a special connection between qubits. Once entangled, they behave as a single unified system, even when far apart. Their fates become intrinsically linked. Imagine two magic spinning coins. You prepare them in a linked state and give one to a friend far away. You both stop them at the same moment. If yours lands on heads, you know with 100% certainty your friend's is tails, and vice versa. This is the essence of entanglement. This does not mean information travels faster than light. It implies a deeper, non-local connection, two parts of a single correlated system. In a quantum computer, entanglement lets qubits work together in sophisticated ways, creating complex correlations classical computers cannot handle efficiently. Superposition gives a vast parallel workspace. Entanglement ties that workspace together, enabling complex, multi-part calculations. Section 6. The power duo, superposition and entanglement at work. Now that we have met superposition and entanglement, let us see how they work together. A quantum algorithm is a carefully designed sequence that uses these properties to find a signal hidden in a massive computational space. It is not brute force checking, it is using quantum mechanics to quickly narrow the search. Classically, one runner tries one path at a time. Quantumly, the runner creates countless copies, exploring all paths at once. Interference cancels wrong paths and reinforces the right one, so when we finally measure, the correct answer is likely. At measurement, the system collapses from superposition, leaving a high probability of the correct path. A classical computer walks every path. A quantum computer senses the entire maze at once and makes the solution path stand out. This fundamentally different approach unlocks new possibilities for real-world problems. So, what does this powerful new way of computing mean for our lives? What kinds of real-world problems can quantum computers help solve? One of the most promising areas is in medicine and drug discovery. Finding a molecule that fits a target protein is astronomically complex. Accurate simulations overwhelm even top supercomputers. Molecules are quantum systems. A quantum computer speaks the same language and can model atomic interactions with higher fidelity. By harnessing superposition and entanglement, it explores many configurations at once, spotting promising candidates faster. The same applies to materials. Stronger alloys, better catalysts, improved conductors for batteries and solar cells. Designing from the ground up means simulating quantum behavior directly, predicting properties before any lab work. For example, quantum simulations could discover a low-energy catalyst for nitrogen fixation, cutting costs and emissions in agriculture. These problems do not just need faster machines, they need a new kind of computation that accurately models the quantum world. Beyond simulating quantum systems, quantum computers can tackle complex optimization problems, finding the best solution under constraints. Shipping routes, airline schedules, and investment portfolios are all optimization challenges. As variables grow, combinations explode. Classical methods often settle for good enough. Quantum explores many possibilities at once. Quantum optimization could drive major efficiencies in logistics, finance, manufacturing, and energy grid management, saving billions and reducing waste. In AI, many tasks involve pattern finding and parameter optimization. Quantum algorithms may speed up specific parts of that process. Quantum machine learning could enhance pattern recognition, improving diagnostics and training more sophisticated systems. Quantum computers will not replace classical AI. They will act as specialized co-processors, offloading bottlenecks in larger workflows. The same properties can break many current encryption schemes, spurring a global push for quantum-resistant security. To realize these benefits, we must build and protect delicate qubits from the noisy world. While the promise is immense, building and operating quantum machines presents enormous challenges. Qubits are incredibly delicate. Their fragile quantum states, superposition and entanglement, are disturbed by vibration, tiny temperature changes, or stray electromagnetic fields. This is decoherence. When decoherence strikes, the qubit collapses to a classical value and the computation is ruined. To protect qubits, we isolate them in dilution refrigerators, cooling chips to a fraction of a degree above absolute zero, and shielding from interference. This makes current quantum computers large, expensive, and difficult to maintain. Even with shielding, qubits are error-prone. Researchers are improving qubit quality and developing quantum error correction codes. Multiple physical qubits represent a single, more robust logical qubit, detecting and correcting errors without destroying the computation. Approaches include superconducting circuits, trapped ions, and photonic qubits, each with unique strengths and scaling challenges. A global race is underway to build large-scale, fault-tolerant quantum computers capable of solving real-world problems. We have journeyed from the simple light switch of a classical bit to the spinning coin of the quantum qubit. We have seen how superposition allows many possibilities at once, and how entanglement creates powerful, spooky connections. Quantum computing is not magic. It is computation based on the universe's fundamental laws at the smallest scales. These machines promise to accelerate discovery in medicine, chemistry, and materials science, and offer new lenses on optimization in logistics and finance. They also challenge us to build a new foundation for cybersecurity to protect our data in the future. As we stand here on October 20th, 2025, we are still in the early days. Large, fault-tolerant machines may be a decade or more away, but the journey has begun. Understanding the basics today prepares you for tomorrow. Read an accessible book, watch a clear explainer, and try interactive quantum simulators. The quantum revolution will be built by people from all backgrounds: scientists, engineers, software developers, ethicists, and business leaders. The most important tool is a curious mind. What are you most excited for quantum computers to solve? Share your thoughts below. If you are ready for the future, smash that like button and subscribe for more tech deep dives. Your quantum journey starts now.